Hello everyone, welcome to the lecture series. So for the design of digital circuits, today's session is introduction to number system. So the role of number systems in digital systems is these number systems are the frameworks for representing and manipulating the numerical data in a digital systems, which enabling computers to process informations like calculations, data storage, and then communication. So here the represented informations in a discrete form. It provides means of quantifying the information by processing the digital system. The main purpose of this which provides a structured way to quantify and encodes real world data, for example measurements and instructions likewise, so which is into format the digital circuits can interpret, typically using binary due to its compatibility with electronic states like on and off conditions. So the main importance of this number systems are fundamental to the digital processing, as they define how the data is stored and manipulated and output. So without them, the digital systems could not translate physical quantities into actionable informations. For example, we take it as a digital calculator, right? So the numbers entered by the user are converted into binary for arithmetic operations, ensuring the accurate computations. So here these are the some number systems: positional number systems, number system conversions, binary codes, and then arithmetics. So these are all the some number system formats. So positional number system is concept of a radix, that is we called as base. So positional number system assigns a value to digits based on their positions relative to the decimal point, which each positions having a weight determined by the system's base. So base is nothing but the number of unique digits in the system, including 0. Like for example, base 10 has the digits of 0 to 9, and base 2 has the zeros and 1. Likewise, base 8 is the 0 to 7 likewise. So the position of a digit determines its contribution to the numbers value scaled by powers of the radix. So the structure of these numbers are written as sequences of digits with integer positions right left of the decimal point and fractional positions right of the decimal point. So each multiplied by the radix raised to the specific power. So the positional systems allow efficient representation of numbers, making them suitable for digital circuits that rely on structured data processing. So so this is the number system for positional number system for decimal, that is the base of 10. So here base, or we called as radix, is 10. So 10 means 10 digit, that is 0 to 9, 0 1 2 3 4 5 6 7 8 and 9. So here we are giving one example, 536.159 base of 10. So each value of this integer part and fractional part is multiplied by the base of 10. Okay, so in general, a decimal number with n digit to the left of the decimal point and num digit to the right of the decimal point is written as an-1, an-2 to a1 a0 dot, which has fractional values a-1, a-2 up to a minus m. So where ai is the coefficient in between 0 and 9. Okay, so which denotes the weight, that is the base of the weight value. So here we consider r as a radix, n is the Here n is the number of integer digits and negative indices represent the fractional digit. Each digit's value multiplied by the radix raised to the power of its position. So this formula applies to any base like decimal, binary, hexadecimal, octal. So by providing a universal method to compute a number's value. So these are all the like fractional side is a LSB, that is least significant bit, and integer side is a most significant bit, that is MSB. We take another one example in a base of 10 for 123. So 1, 2, 3, each the number can be multiplied by 10, the base of 10, with 10 power 0, 10 power 0, 10 power 1, and then 10 power 2, illustrating the positional weighting. So this positional number system having these coefficient values, let R is the radix or base of the number system, let XC is a character from the character set of the radix, and then n is the number of represented by radix. N, small n denotes the integer portion of n, and small m denotes the fractional portion of the n. So it is given here as the formula. So this is also another one example. For example, we take R is equal to 6. So the radix value 6 means what happened is given here. The conversion from n radix to decimal follows similar process as above. So the most common numbers in the decimal number system is base 10. We already seen that. The decimal number system or base 10 uses 10 digits, is standard system for human arithmetic due to its alignment which counting on 10 fingers. So like the structure of this digit position correspond to a power of 10, which position to the left of the decimal point representing whole numbers. For example, 10 power 0, 10 power 1, 10 power 2 up to 10 power 9. This position of the right representing the fractions like 10 power minus 1, 10 power minus 2 up to whatever the values we taken. And then common in everyday applications like financial calculations, measurements and user interfaces, but digital system often convert decimal inputs to binary for processing. For example, we take the number for 536 means for the decimal numbers base of 10, we consider the values of each number into multiplied by the base of the weighting the value. So this breakdown of decimal number into a positional components is shown in the before slides. So the example demonstrates how the positional system assigns weights to digit, a concept that extended to other bases like binary which preparing for later discussion on number conversion.